Is the mic okay? Can everybody hear? Well, standing in front of that one, so of course it's okay. So I imagine lots of people are familiar with some concepts about randomness extractors, but I will go through the whole thing to make sure that everybody can follow. So if there's some question, please don't hesitate to interrupt. First, so what is a randomness extractor? Hand-waving definition is a function which transforms a large but weak source of randomness into a shorter uniform distribution. This has loads of applications. I just did a copy-paste from some review paper. I put it on the column on the right, some of the applications in the quantum case. Okay, tiny pointer. Is it this actually visible? The laser pointer? Okay. Quantum case, it's used a lot for, well, in privacy amplification, for QKD, it's an essential step. All protocols for randomness expansions, randomness recycling, all constructions of pseudo-random generators, they all use some form of extractors. And then it has a whole bunch of other applications in complexity theory. So it's been a very well-studied topic in classical computer science. And so the basic idea is we start off with a random source which is non-uniform but rather long, n is long, and we want to map it to some source which is uniform but has length m. Now this can't be done with the deterministic function x, so we need a random function, or what is usually done, the randomness is modeled as a second input. So now we have a deterministic function which takes two inputs. This is a short, what is usually called a seed, and it allows us to produce some uniform output, or close to uniform. So the definition in the classical literature, so here I'm only talking about classical function, classical inputs and outputs for the moment. It would be a function which takes these two inputs, one long of length n, a short seed, and produces this output. And we say it's a k epsilon extractor if two things have to hold. Firstly, the probability distribution of the output has to be close to the uniform distribution, so with some error epsilon. And secondly, we want this to hold for all distributions x which have some min-entropy k. So this is a really key point. We generally don't know what our input distribution is. If we knew what the input distribution is, then it's trivial. You can do this deterministically for every input distribution. But we don't actually know the distribution. The only thing we know about it is a bound on some form of the entropy. Haven't put up the exact definition of the min-entropy because it's a technical detail, but I'd be happy to explain after in the break if people have technical questions. And there's a different version which is called a strong extractor. When this randomness which is used here, the seed, we sort of get it back. It's kind of a catalyst which we get back at the end. So now the only difference in the definition is now we don't want only the output to be close to uniform, but the output concatenated with the seed y should be close to the uniform distribution concatenated to the seed. But now in most applications where we want to use extractors, there's always some kind of side information present. So a typical application, the one used in QKD, is where in some setting where somehow two honest players receive some string x, and there's some dishonest player with some side information e. How we got into that situation, we don't care at the moment. We can do this in QKD. We can do this with some noisy source or noisy channels. There are many settings which allow us to arrive in this situation. And the only thing we know about the adversary's information, we have some kind of bound on the entropy of the strings that Alice and Bob know conditioned on this side information E. And what they want to do is extract some secret key which is uniform. They want to extract that from X. So what they do is Alice generates this random seed, and she makes it public. So she sends it to Bob, but then the eavesdropper also gets a copy. And then they apply an extractor to X using the seed Y, and they get some output Z. And we would like this Z to be uniform and also to be unknown to the adversary. So we need a definition which is slightly different from what I showed on the previous slide. Supposing for the moment that E is classical distribution, we now what we want in this case for this application, we actually need the stronger version. We want the output to be close to uniform, but also independent from the side information E. So now our bound, it's not just a bound on the min-entropy of X, but also the min-entropy of X from the point of view of the adversary. So you can think of this as an alternative or different definition of extractors if we have classical E. And if we have quantum E, we can define a quantum proof extractor to be a function such that the same thing holds, but now for states which are classical on X in quantum on E. So for all states, classical on X, quantum on E, which have this bound on the min-entropy, we want the output of the extractor to be close to uniform and independent from the adversary's information, either in the weak case without the Y, without the seed, or in the strong case with the seed. So now I've just shown you 3 definitions of extractors. So of course you might be wondering what's the relation between these definitions. So I've just quickly summarized them here in the weak case. And of course a quantum proof extractor is also a classical proof extractor because it includes classical side information as the special case. And classical proof extractor is, of course, an extractor because it covers the trivial case where there's no E. What's interesting is the bounds going in the other way. Now, it turns out that an extractor is also a classical proof extractor with very similar parameters. They're just minor changes here. But when we want to go from a classical proof extractor to a quantum proof extractor, the best bounds we have at the moment is that there's some exponential loss in the error, which is exponential in M in the output. There are different bounds where you have something exponential in other parameters, but I need this one for the rest of the talk. So we have this exponential bound, and it's actually still unknown how whether this is tight or not, because we don't have any examples of classical proof extractors which fail with this huge error in the case of quantum side information. So we don't know yet if this is tight, but this is the best bound we have at the moment. So this is the picture for randomness extractors, and what the work is about two-source or multi-source extractors. So if we go back to our extractor, so the definition of the simple extractor I had on the very first slide, it looked like this. And I can write it slightly differently. Instead of saying we have our source which has min-entropy K and a uniform Y, I'm saying we have a source now which is this, which has 2 parts, 2 independent distributions X and Y, such that the min-entropy of Y it has full min-entropy, so basically it's uniform. So that's exactly the same thing. And now the definition of a two-source extractor is a minor relaxation of this. You basically copy-paste this, but instead of having min-entropy of Y is uniform, you just have a lower bound on the min-entropy. So a two-source extractor is just this relaxation of an extractor. So one minor change in definition, and it's a very useful relaxation because, when we have something which is perfectly uniform. So it would be very nice to have something like that also in the quantum case. So if we put all these definitions together, we have our extractor, our classical proof extractor with classical side information, quantum side information, and we have this definition. And the question is, well, how do we relax these definitions in the case of side information? And one of the main contributions of this work is providing definitions for this, which seem to be natural generalizations of this to side information. So before telling you how we did it, I'm going to show you an example of what kind of goes wrong if you try and do it in the most straightforward way. So a reasonable thing to do would be to say, okay, when we don't have side information, we need X and Y to be independent. So let's keep X and Y independent. We don't want our two sources to be correlated. And instead of having a bound on the entropy of X, just X, we have now entropy of X given E and entropy of Y given E. So a candidate definition would be, and here I'm just doing classical E for the moment, because this definition actually fails just with the classical E. We could try and say for all tripartite states which satisfy these properties, we want the output to be close to uniform. And we can construct an example which shows that this definition is impossible to satisfy. So if someone claims to have an extractor which satisfies this, we can find a counterexample. We can construct a distribution which satisfies this and has a big distance. And this was already done by Kasha and Kempe in 2010. It was the first paper on two-source extractors where they realized this is sort of non-trivial. So the example is as follows: take X and Y to be uniform independent n-bit strings, and we're going to make the side information be just 1 bit. So we apply the extractor to X and Y, and we just take the first bit of the extractor and we give that to the adversary, which means we still have a lot of entropy, both in X and in Y, and yet the distance from uniform has to be at least 1/2, because here we have a perfect correlation and here they are independent. So a trivial definition like this just doesn't work, and we need to think a bit more of how to do it. So the definition I wrote for the two-source extractors was this one. For any independent x and y, we just have bounds on the entropy of x and y. So this we could write slightly differently and say for any joint distribution of x and y which are independent, which basically have no the conditional information between x and y is 0, these should hold. So this is exactly the same definition. And if you write it that way, then there's an obvious way of adding side information, is to say, okay, well in the classical case, with the no side information case, we just asked x and y to be independent, and now we ask x and y to be independent given e. Just this tiny minor change, we add e. So this would be the definition of two-source extractors with classical side information. We really want x and y to be independent from the point of view of e, and we want the min-entropy of x given e and y given e to have some bound on it. And we call this in the Markov model because this kind of state is called a Markov state. And then, of course, you can do the same thing in quantum. Take a quantum Markov state. So states, we still have x and y as classical, but e is quantum. Any state which satisfies this, and we just put our quantum state here. So now, what are the relations between these extractors? Again, we trivially have that a quantum proof two-source extractor will be a classical proof two-source extractor, which will be a two-source extractor. And what we did is write proofs for the other direction. So the first one, we get exactly the same as for the case of seeded extractors. Basically, if you want to go from here to here, we need a little bit more entropy in the source to be able to extract the same amount. So there's just this little increase in the term of in log of 1 over epsilon, and a small constant factor here in front of the error. And so any extractor, any two-source extractor can also work when you have side information, if it satisfies this Markov state property. And now our main theorem is a proof of what happens in this case, and we get a very similar bound. We have again something which is exponential in M. So the entropy of the two sources stays the same, but we have an exponential blow up here in the error. Now, unlike the case of seeded extractors, where you can't actually do much with this exponential blow-up prevents you from getting any interesting constructions. I'll be explaining later during the talk how we can actually get interesting constructions even if we have an exponential blow-up just from this theorem. But before getting to that, I will give a brief sketch of how the proof goes. It goes in two steps. In the first step, we consider only sources which have this form. So very nice, our side information E is split in two parts. Part is correlated to one of the inputs, and part is correlated to the other inputs. And now what we want to do is upper bound. So I'm just giving a sketch in the case of the weak extractor, but it's the same idea in the case of the strong extractor. We would like to upper bound this amount. And what I'm going to start by doing is actually lower bounding it. And then I'm going to show that my low bound isn't actually that bad. So to lower bound it, we look at, the trace distance between this and this is simply the maximum of all possible measurements. I'm going to look at one specific measurement, which consists in measuring the side information E in order to try and guess X and Y. So the measurement we actually use is a pretty good measurement. So we measure E1 trying to guess X, which gives us the outcome Z1. And we measure E2 trying to guess Y, and we get the outcome Z2. So you do the same on. So we basically apply this measurement, so it's a CPTB map if you want. So we can only decrease the trace distance. And now that we have this, we're going to try and guess what the output of the extractor is by simply applying the extractor to this Z1 and Z2. And then we bound how good our guess is. So if you want to apply a function to this which maps to 0 if the two here are equal and maps to 1 if they're not equal. And then you look at the statistical distance between the two and you get some bound P. Okay, so this is a lower bound. Now the main technical part in the paper just consists in showing that this lower bound isn't that bad. Well, actually it's quite bad because it's exponentially bad, but this satisfies our purpose. So I'm not going to say more about it now. It's just have to do the calculations the hard way, and you show that this bound is it's also an upper bound if you have your 2 to the m here. But now where this gets interesting, because what we want to prove is that if we have classical side information, then we can extract if we have quantum side information with an error which is increased by that. And we have up here that this state here, which has classical sign information, is bigger than P. So if you just plug that into this, and we know that this is greater than that, which is then greater than this, and this is a state which only has classical sign information. So if you assume your extractor works with classical sign information, you know that you have some epsilon here. So we get this exponential upper bound. Now everything, oh, sorry, that was just the first part. So second part, because it was just for these states which have product form. So now we want to generalize it to all states which have conditional mutual information, which is 0. And here there's this very nice theorem due to Hayden, Joshua, Petz, and Winter, which says that any state, so here even A and B quantum, the theorem, I mean, we only have X and Y classical, but it works for quantum. If the conditional mutual information is 0, then the state can actually be written as this direct sum of states which are in product form. And so we basically just plug that into the theorem, and then we can generalize it to all states, because we have actually proven this special case. So now, what I told you was for two-source extractors, and this can actually be generalized to multi-source extractors. So we don't only have two sources. We have, say, L sources from X1 to XL, which are independent, and we have a bound on the min-entropy of each source, and then we just want the output to be close to uniform. And this we can generalize in exactly the same way. All the sources are independent. It basically means that every source xi is the mutual information between xi and all the other x's must be 0. So we just now add an e here, and we get a generalization to quantum sign information with multi-sources. And the proof goes through in this case as well. So now we go back to the theorem. We have this exponential blow-up. And if we actually want to use this to get a useful construction, that means you have to start with a construction where epsilon is exponentially small. And there's this bound on the size of the seed, which has been done for seeded extractors, but then of course it also works for two-source extractors, which says that the size of the seed, in this case, is lower bounded by this. And the term we're actually interested in is simply this one. So if we want to get something which is exponentially small here, if we say plug 2 to the minus m in here, we'll find that our seed has to be greater than 2 to the m. And that's why an exponential blow-up like this is not very useful in the case of seeded extractors, because we could only get results for extractors which have a very long seed, and those we actually understand extremely well. It's all the universal hash family and almost universal hashing, dual universal hashing, they all have this property, and we have very good bounds on them without this exponential loss. So a kind of theorem like this in the case of seeded extractors wouldn't make us gain anything. However, in the case of two-source extractors, D here is a bound on the length of the source. It's not a bound on the entropy of the source. So it's still extremely useful because we have constructions which maybe have a very long source but very little entropy, and that's what we're interested in. We're interested in extracting from sources which have very little entropy. So there are several extractor constructions which actually have an exponential small error. So if we plug our result in there, we get very good construction. So I'll give you one example here. It's an extractor by Ratz, and it requires one of the sources to have entropy at least, so n would be the length of the source. And the entropy of one of the sources has to be at least n half plus some small delta, and the other source just needs a logarithmic, and entropy just has to be logarithmic in its length. And it has this error which is exponential in m. So you plug our theorem in that, and you basically get an extractor which has the same parameters except for the constants. This delta prime is slightly bigger than delta, and this c prime is slightly bigger than c, and here our constant in the exponent has changed. But we really have the same regime of parameters in the classical case, in the quantum case, even though this bound has this exponentially bad error. Now, not all constructions have this nice behavior. There are constructions, interesting constructions, which don't have an exponential error, so an exponentially small error. So what if we have an interesting construction that has an error which is bigger than 2 to the minus m? So we can't directly apply the theorem, but what we could do is, well, we can't apply it to the same parameters. What we just do is we shrink the output, because since our blow-up, it depends on the output length, we just output less. So, for example, if we pick an output m prime which has this length, and you plug that in here, we will still get roughly the same error, but now, of course, we get a shorter output than the original extractor. But this is still very nice, because if you get a short output, you still have a uniform output. So now we can plug it into a seeded extractor, because we know we have constructions of seeded extractors which only need a short seed, for example, Trevisan's extractor. So once we get this output m prime, if it's strong, so we need this extractor to be strong for the output to be independent from the source, or from at least one of the sources. We just now run a Trevisan's extractor on the same source with the output of the two-source extractor, and then we were able to extract all the entropy from one of the sources. So we get the following constructions. So this is a three-source extractor by Lee. So this is very recent. It just got published this year in Stock. So there are lots of recent results that are coming out in classical, still in classical extractors. And he has this nice three-source extractor where the very low requirements on the entropy on the sources. There's just some polynomial in the logarithm of n. So each source, for simplicity, I just took the same n, but actually lots of these constructions work for sources of different length. So the only requirement on the entropy of the source is that the entropy k is lower bounded by at least this for all three sources. And his construction can extract something linear. If I'm not mistaken, it's maybe even k minus small o of k, but nearly all of k is extracted. And it has this error, which is not exponential, it's sub-exponential. But sub-exponential is still very good. So if we apply the trick that I explained on the previous slide, and we get a quantum extractor, which now doesn't extract everything, because if not, the error would just blow up and it would be constant. But we can extract something which is sublinear. So this sub-exponential error directly